In this video, we're going to talk about acid-base indicators, what they are and how they work, and how we can use them to determine approximate pH ranges of unknown solutions. So indicators, they're a complex weak acid or base compound that changes color depending on the concentration of hydronium ions that are in the solution that they get added to. Now, most indicators are organic acids and they have pretty big structures, so oftentimes we abbreviate their formulas. So if we go to our data booklet, okay, and we go to page 10 here, we have a list of indicators. Now, the abbreviations that they're talking about are in the second column underneath suggested abbreviations. So for methyl violet, the abbreviations that we'd be using are either HMV or just MV with a 1- charge there. Okay, now the reason why there are two different suggested abbreviations is because one of these abbreviations, like the one with more hydrogens in it, is going to be the acidic form of this indicator, and the other one is going to be the quote-unquote basic form of the indicator. Now, the reason why this is important is because the acidic form of the indicator is one color and the basic form of the indicators are a different color. And these differences in colors help us to figure out what pH range a solution can be. Now, how you read this table here is with the pH range, the left-hand number is going to correspond with the left-hand color, whereas the right-hand number is going to correspond with the right-hand color. So what that means for here, I'm going to use a different example just so that it makes a little bit more sense, just because you can't get much lower, at least in the context of Chem 30, than 0. But looking at, let's say, orange 4, what this means is at a pH of 1.4 and below, orange 4 is going to be red. At a pH of 2.8 and above, orange 4 is going to be yellow. And if the pH of the solution you're adding orange 4 to is somewhere in between 1.4 and 2.8, then it's going to be the in-between color, in between red and yellow, which is going to be orange. Okay, so let's just talk about that for a little bit here. Okay, so like I said, acid-base indicators, they show an endpoint of an acid-base titration, which is how it helps us to determine the approximate pH of the solution. Okay. So I'm going to go through the rest of these points and then I'll get to what I was talking about colors, because it is quite useful to review the color wheel in terms of knowing what color the quote-unquote in-between color will be. Okay, so indicators are always in the same form. They're either acidic or basic as the solution they are in. Okay, so we use the HIN as a general formula for the acidic form of an indicator, whereas IN 1-, so that's just indicator with a 1- charge, is the general formula for the base form of an indicator. Okay, so like I said, the acidic form of your indicator is going to have one color, whereas the basic form of your indicator is going to have a different color. So now let's review the color wheel so we can get into it a little bit more. So we're going to start off by drawing a circle, and then we're going to draw an X through that circle and then a horizontal line going through the X. Okay, so with our color wheel, we've got our primary colors, and those primary colors are blue, yellow, and red. So they're kind of like your beach ball colors that you'd see. Okay, now the other three wedges here, they're going to represent our secondary colors. So those are what you get when you mix two of the primary colors in together. So your secondary colors, those are going to be green, orange, and purple. So green, you get that if you mix blue and yellow together. Orange is what you get when you mix yellow and red together. And then purple is what you get when you mix red and blue together. Okay, so this color wheel is going to be very helpful for us, just even as a review there, to help us kind of decode our data booklet or the table with the indicators on it. Okay, so let's say, for example, I go to bromocresol green. So the acidic form of bromocresol green, or the abbreviation for it, is going to be HBG, whereas the basic form of it is just Bg with a 1 minus charge on it. And its range is 3.8 to 5.4. So what this means is that at a pH of 3.8 and below, bromocresol green is going to be yellow. And at a pH of 5.4 and above, bromocresol green is going to be blue. And now, if you have a solution in which you add bromocresol green to it, and the pH of that solution is somewhere in between 3.8 and 5.4, then bromocresol green, since the pH is in the in-between range, the color of bromocresol green is going to be an in-between color between yellow and blue. So that's going to be green. So just to give you a visual here, I'm going to add a picture here. All right, so this is bromocresol green. Right, and as we said from our data booklet, at a pH of 3.8 and below, bromocresol green is going to be yellow. So we can see that here. Okay, the only difference between this top row and this bottom row is how many drops of bromocresol green indicator that they have added. Okay, but this 3.5, that represents the pH of the solution in this column here. Okay, so as we can see, because it is at a pH of below 3.8, bromocresol green is yellow, which matches up with what our table says. Okay, now for the next few here, so looking at our table, at a pH between 3.8 and 5.4, we can expect bromocresol green to be varying shades of green, which is what we see for these next three. Okay, so these two are a bit more like green than this one, and the only reason for that is just because this last one here at a pH of 5, because it's getting closer to the more blue side of the range for bromocresol green. That's why it has more blue in it, because there are more moles of the basic form of bromocresol green in there, which is why it is appearing more blue. Okay, but for the in-between range, you have a range of different greens, but for the purposes of this course, we kind of just call all of the solutions within this range between 3.8 and 5.4, we call it just green, just for simplicity's sake. Okay, now at a pH above 5.4, okay, so at 5.5 and 6, these are blue. Okay, which matches up with what our chart says is going to happen when we use bromocresol green. Okay, so the endpoint of indicators that occurs within the range that's talked about in the data booklet here. Okay, so the endpoint occurs somewhere for bromocresol green between 3.8 and 5.4. That's just because bromocresol green is really good at telling you the pH of a solution when it's in this narrow range. It can't tell you the exact pH, but it can tell you at least a smaller range than using something like litmus paper. So as we previously discussed, okay, when an indicator is in a more acidic solution, it will react with that solution to produce the more acidic form of that indicator, which is going to be a specific color. So for the example of bromocresol green, the indicator reacts with the solution to produce more acidic molecules of the bromocresol green indicator, which turns the solution a yellow color. That's what this part is saying here. Okay? But keep in mind, when we say an acidic solution, we're meaning like sometimes for some indicators, it's not going to be like a pH below 7. We're meaning like a more acidic solution. Okay, and then when you put the indicator in something that's more towards the basic side, then the indicator, the acidic form of the indicator, will react with the solution to produce moles of the basic form of the indicator. Okay, so yes, our notes do say like you put an indicator in an acidic solution, but we're really meaning like it's a solution that's more towards the acidic side will produce molecules of the acidic form of this indicator. The reason why I specify this is just because if you have an indicator such as let's say thymolphthalein, so it has a pH range of 9.4 to 10.6. Okay, so the acidic form of thymolphthalein, you'll get that at any pH at 9.4 and below. Okay, and that acidic form of that indicator is going to be colorless. So even though, like, let's say we had a solution where we put thymolphthalein in it and it was a pH of 8, let's say, the acidic form of the indicator will exist and like the solution will be colorless, even though like the pH of the solution at 8, it's still a basic pH, but it's more towards the acidic side compared to like a pH of 10.6. Okay, so for indicators where it goes from a range of colorless to some other color, Okay, let's get into that just for a quick second here. So at a pH of 9.4 and below, thymolphthalein will be colorless. But at a pH of 10.6 and above, it's going to be blue. Now the in-between color, in between colorless and blue, is just light blue. Okay, same for something like phenolphthalein. The in-between color between colorless and pink is going to be light pink. All right. Now, with looking at page 10 of our data booklet, you may have noticed that our indicators in the last column, they have Ka values associated with them. Okay, so since we have the Ka values for all of these indicators here, okay, so they're going to correspond with the acidic form of the indicator. So I'm just mentioning that because some of these indicators have more than just one color change. So an example would be thymolphthalein. It goes from red to yellow and then yellow to blue. So remember Ka, that's the acid equilibrium constant. So it's going to be associated with the acid form of the indicator. Okay, so the acid form for thymolphthalein, or sorry, for thymol blue, at least in this first row here, you're going to find that at a pH of 1.2 and below. So the Ka is associated with the more acidic form. Okay, and since we have the Ka, that means we can also calculate the Kb. So, for example, what is the Ka for bromothymol blue, and what is the Kb for the basic form of that same indicator? So let's look that up here. So bromothymol blue is right here. So the Ka for it is 5.0 times 10 to the negative 8. All right, so now that we have Ka, we can calculate Kb. So just as a quick reminder, this formula you do not have given to you. You are going to have to memorize it. So you can start off with Ka multiplied by Kb is going to give you Kw. So if we rearrange this by isolating for Kb, we can divide both sides by Ka. So the formula that we're going to be using is Kb is equal to Kw divided by Ka. So Kw, remember that that is a constant, and that constant is given to us. That's going to be found on page 3 of our data booklet. Right here. So it's the water autoionization constant, and it's 1 times 10 to the power of negative 14. And then in the denominator, I'm going to put my Ka value. And now let's calculate it. So 1 times 10, so I'm getting the times 10 by going second function log, and then negative 14, hit the right arrow to get out of the exponent, close the bracket, divide by bracket 5 times 10 to the negative 8, hit enter, so we get 2 times 10 to the negative 7. Now, since both of these values that we used are constant, or are constants, It is a little bit difficult to determine sig values, but like if this is on a test, it would tell you like how many sig to round off to. So for now, we're just going to not worry too much about sig and just say that we're just going to round to 2 sig for our answer here. But just know on like a test or an assignment, it'll tell you how many sig to round off to if all of the numbers that you're using are constants. Okay, so this KB value, it is associated with the basic form of our indicator here. All right, the other types of questions that you can get that involve indicators is having to use some data from indicators to determine what pH range an unknown solution is. So for this next example, we're asked, what is the pH of an unknown solution that is colorless in phenolphthalein, yellow in methyl orange, it's yellow in bromothiamyl blue, and then it is blue in bromocresol green. Okay, so I've underlined certain parts in different colors just so you can track where all this information is coming from when we answer this or as we're figuring this out. Okay, so first off, I'm going to draw a number line here. And you got to understand that when you're given these types of questions, with how this question is worded, the color comes first, and then the name of the indicator is coming second. Okay, so when it says yellow in methyl orange, orange is not the color of the indicator. That's part of the name of the indicator. So this is the color of the indicator, and methyl orange is the indicator. Okay, it's same deal for yellow and bromothiamyl blue. Yellow is the color, bromothiamyl blue is the indicator. Okay, blue is the color, bromocresol green is the indicator. Okay, I'm actually going to make this line a little bit longer here. Okay, so let's start off with our first indicator. So it's colorless in phenolphthalein. So we're going to find our indicator on page 10. So I'm just going to clean this up a little bit here. So phenolphthalein is right here. So since we were told it's colorless, that's the left-hand color, so it corresponds with the left-hand number. So phenolphthalein is going to be colorless at a pH of 8.2 and below. So let's record that in our work here. So I'm going to write 8.2, and then I'm going to draw an arrow saying and below. Okay, let's move on to the next one. So we've got yellow in methyl orange. So let's find where methyl orange is. Well, methyl orange is right here. So it said yellow. So yellow is the right-hand color. So that corresponds with the right-hand number. So at a pH of 4.4 and above, methyl orange is going to be yellow. So let's color code this properly. So I'm going to go 4.4 and above. For the next one, that's yellow in bromothiamyl blue. So let's find bromothiamyl blue. So yellow is the left-hand color, so it corresponds with the left-hand number. So at 6.0 and below, bromothymol blue is going to be yellow. Okay, and then last but not least, we have blue in bromocresol green, so let's find that. So blue is the right-hand color, so it's going to correspond with the right-hand number. So at a pH of 5.4 and above, bromocresol green is going to be blue. Okay, so this is what we just did. That's all of our work for this question. Now, how you can figure out what the actual answer is you just look for the closest two arrows that are pointing towards each other. So that would be these two right here. And that tells you that the range for this solution, so the range of possible pHs, are between 5.4 and 6. So pH is between pH of the solution, I should be saying. Okay, what I'm going to do before I say my final answer is I'm just going to write out what I said, just getting to this point here. So we're getting our information. About indicators. From page 10 of the data booklet. And to get your answer, you're finding the closest arrows that point towards each other. Okay, now the question does ask us, what is the pH? Okay, so basically it's asking for a specific number, because right now what we have here is a range. The question is asking for one singular number to represent the pH of the solution. So technically speaking, you could pick any number between 5.4 and 6, but just to kind of say a specific procedure to follow, what you can do is you can take the difference in between 5.4 and 6, and then you can just divide that by 2. Okay, so the difference between 5.4 and 6 is 0.6. 0.6 divided by 2 is 0.3. So that 0.3, what I'm going to do is I'm going to add it. You can either add it to the lowest value or subtract it from the highest value. Either way is fine. So 5.4 plus that 0.3, that's going to give us 5.7. So we can say the pH of the solution is approximately 5.7. Okay, so if you wanted a cut and dry procedure to figuring out one specific pH, you could take the difference in between what your range values are, divide it by 2, add it to the lowest value, and get your singular pH number. Or alternatively, like what would still technically be correct is any number within the range here. So if you said 5.5, 5.6, or 5.9, like any of those would also still be correct according to the range that we figured out. Okay, but again, if you want a cut and dry solution or procedure for figuring out a singular pH for an unknown solution, there you have it.